one equivalent adding into the carbonyl, generating HCl, and the second equivalent to soak up the HCl, just like this. So to be fully correct, we need two equivalents, 2.0 equiv of the amine, for the reaction to be really forced to completion. And that would give us the added plus the HCl salt of the other equivalent of amine. But still, with respect to the attack, I mean, from the tetrahedral intermediate, it's going to much favor to kick off Cl minus than the amine because of the pKa's. So does that make it clear about how we can predict where the equilibriums will lie? It will always lie on the side of the weaker nucleophile, swimming around in solution on the stronger nucleophile, being part of the acyl group. I hear some murmuring. Is there, yeah?
Does the tertiary hydrogen not work if there's no hydrogen?
Exactly. Yeah, so it's always, so when it adds, it's be the ammonium. And so we don't get that stabilization. It's always neutral, so yeah. And I hear more murmuring.
So the higher pKa always attaches.
Higher pKa, meaning it's a stronger base, is going to, the equilibrium is going to favor the stronger base forming the bond. So let me show you some examples. And so in this class, in this chapter, in this part of the chapter at least, we're going to focus on several different carboxylic acid equivalents. So we started out with acid chlorides. We have acetic anhydrides. We have esters. And of course, in this case, if this R prime is H, what functionality is it? If this R prime is H, this ester would be a carboxylic acid. But pKa arguments, obviously carboxylic acids and esters are way different. But for the sake of our argument here, pKa speaking, water and methanol are very similar, 15.7 for water, 16 point whatever for methanol. So pKa's are about the same, so for this argument, we can treat waters and alcohols basically similar. And then we have amides. All right. Next thing, I'm just going to write the pKa's of the functionality of the acyl group right here. So the pKa of HCl, which is the conjugate acid of the group here, of the leaving group, pKa of HCl sub-0. I think someone told me -7. I usually use 0 because I think of HCl being aqueous conditions, and you probably pretty much can't get less than 0 in aqueous. Well, you can, but I usually just say 0 in my mind. But let's say sub-0. So pKa is pKa less than 0. This part, boxed in red, is a carboxylate. Conjugate acid is carboxylic acid. Carboxylic acid, pKa, about 4.5. Leaving group here is an RO minus. ROH is an alcohol, pKa of about 16. And as Jasmine pointed out, the pKa of an amine, neutral amine going to the anion, is about 36. So based on the pKa argument, what this says is, we can take an acid chloride to an anhydride by throwing in our carboxylate. Yeah, makes sense. We can take an acid chloride, do an ester by throwing in an alcohol. And based on the pKa argument, we know the equilibrium is going to vastly prefer the ester because alcohol is a much stronger nucleophile. That's what's going to favor here. And then finally, if you take an acid chloride and an amine, we're going to get the amide. And typically for this type of chemistry, we do this in dichloromethane as the solvent. So all of these reactions, we typically work with acid chlorides, we typically do in a polar aprotic solvent. Aprotic being key. So DCM, dichloromethane, is a good solvent. And you can do these all at room temperature or cold. Okay, now what? Well, can we take an anhydride to a chloride? Based on pKa argument, can we take Cl minus and go to the acid chloride? Where would the equilibrium lie? Towards the acid chloride or the anhydride? Towards the anhydride, exactly. So, if I ever ask you, give you a reaction somewhere in an exam or a final that says anhydride plus Cl minus goes to, the answer is no reaction. Or, equilibrium does not favor acid chloride synthesis under these conditions. There are better ways to make acid chlorides. This will be 1 times 10 to the minus 4.5 equilibrium constant, so it's not going to happen. Blah 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 blah. So yes, you cannot take a weaker nucleophile and add it into an acyl group with a stronger nucleophile and expect equilibrium to favor what you want. In this case, the odds are not in your favor. Thank you for someone catching that. All right. However, starting with the anhydride, we can most certainly take an anhydride and throw in an alcohol and get the ester out. Almost certainly. Like the first 3 years of my Ph.D. thesis were actually based on that, which is kind of depressing when you think of that. Considering anyone who talks to me is only wants to talk about my last 2 years. So yes, you can take an anhydride and go to the ester. Or you can take an anhydride and go to the amide, absolutely. That's by throwing in a secondary. So an anhydride can go to an ester or an amide if you add an amine or an alcohol respectively, but it cannot go to a chloride. You cannot go to an acid chloride from an anhydride. And by just comparing the pKa's, you can probably basically say what the equilibrium constant for that reaction would be backwards. So this is kind of redundant. Can you take an ester and go to an anhydride? No. Absolutely not. Can you take an ester and go to a chloride? Absolutely not. The equilibrium is not going to be favored. So I'm not even going to draw those conditions. I'm just going to draw a big red X. But can you take an ester and go to an amine?
Sure.
Absolutely. Just throw in your amine. Here's my question though. If I asked you to give me a synthesis of an amide, would you go from an ester or would you just go from the acid chloride? Yeah, it's better. If I had to make an amide today, using one of these reactions, I'd make an acid chloride. So what this I hope this shows is with these nucleophilic acyl substitutions, the most basic level. And later in this chapter, I'm going to show you how to overcome this pKa argument. And the answer is Le Chatelier's theorem, and I'll explain that as we go on in the chapter. But all things being equal, if you just take a nucleophile and add it into an acyl group and don't do anything tricky, the equilibrium is going to be completely and utterly controlled by the difference in pKa's between the nucleophile and the leaving group. And if you want to impress someone in a talk, you can say, oh, my guess is this would be a KEQ of blank, based on this pKa argument. And then people will say, oh, I wasn't expecting someone to, you to give me that analysis. That's this sophisticated. So remember this. Something is similar in notes. And remember, for simple nucleophilic acyl substitutions, it's all dependent on the differences in pKa's between the nucleophile and the leaving group. Now what? Well, let's start out with, based on this, and not taking into account what I talked about the last 3 minutes on Friday, there's no good way to make an acid chloride, right? With using it, you could not, using a typical nucleophilic acyl substitution, there's no good way to make an acid chloride. So how would you make acid chlorides? The answer is using thionyl chloride. You usually do it in dichloromethane. And thionyl chloride is a sulfur with 2 bonds due to a double bond to an oxygen and 2 chlorines off of it. So thionyl if you take this carboxylic acid plus thionyl chloride, you'll get an acid chloride out. Plus SO2 plus HCl. SO2 is a gas. When it forms, it's going to bubble away. And that's going to allow us to use our good old friend Le Chatelier's theorem that pushes equilibrium towards the acid chloride. So in order to get the equilibrium to favor the acid chloride, you really need Le Chatelier's theorem and bubbling off of SO2 to really push it. So that's the first way. The way to overcome these pKa arguments in nucleophilic acyl substitution is to get good old Le Chatelier on your side. And if you get good old Le Chatelier on your side, you can get away with this stuff. Because, if I just showed you this, you'd say, well, OH, pKa is 16, Cl, pKa of 0. So in theory, this should be a very disfavored reaction based on the pKa arguments. And it is. But Le Chatelier's theorem is a really powerful thing if you guys haven't realized this yet in class. And so let me show you the mechanism. And then hopefully you'll believe me that this does work. Let me do the arrows in blue. So first off, lone pair of electrons on the oxygen will attack the sulfur with the carbonyl. And you know how I say chemists like to draw arrows so that when you attack a carbonyl type, the first arrow forms the tetrahedral intermediate. Second arrow collapses the tetrahedral intermediate. And then the third arrow kicks it off. Can you guys see this? Can you guys see it okay?
Yeah.
All right. I just worry because it's a little lip. So this will attack this, kicking out, eventually tetrahedral intermediate collapses, kicks off Cl minus. And that's going to give us that's going to give us this. This is a carbonyl with a positive charge on the oxygen. Is this going to be an electrophilic carbonyl with a positive charge?
Yep.
Absolutely. It's going to add in, the chlorine's going to then add in, because this is such an electrophilic thing. And of course we'll have some kind of equilibrium species. So we will get a tetrahedral intermediate that looks like this. And frankly, you would almost expect the equilibrium to favor this, kicking off Cl minus, because Cl minus is such a, it's a good leaving group. It's a very weak base. Yes?
There shouldn't be a plus on the oxygen.
Yeah, isn't this a plus right here?
No, but in the previous one, the electrons moved to the oxygen.
Oh, yes, yes, yes. Oh,
That's it.
this is neutral, right?
They're both neutral.
Okay, well, positive charge here. Oh, yeah. Oh, good catch. I'm so used to drawing positive charge on weird things that are about to leave. So we get this intermediate, this tetrahedral intermediate, and we could easily kick the Cl minus F to go back here. But what we actually, the productive pathway is actually kicking this off. And first off, I want to mention, this is, like acyl, almost like a thioacyl group, right? So because of electronegativity and risk, well, let me show you what the leaving group would look like.